Hello everyone! This talk presents my paper entitled From Risk Reduction to Risk Elimination by Conditional Mean Risk Sharing of Independent Losses, co-authored with Michel Denuit. The rule we study allocates to each participant a contribution equal to the conditional expectation of their individual loss, given the aggregate loss of the pool. The central structural question is, when losses are mutually independent, does enlarging the pool always make each individual contribution less risky, and can this residual risk vanish entirely as the pool becomes large? Our approach is deliberately two-layered. First, we work at the probabilistic level and analyze how conditional expectations behave when the conditioning information is replaced by a more aggregated signal. The key intuition is informational dilution. A larger independent sum is a noisier indicator of any single component, so the conditional expectation becomes an average over more scenarios. Second, we translate these stochastic statements into actuarial consequences. We obtain monotone diversification results expressed through convex order, and we provide explicit structural criteria ensuring that the variance of contributions tends to zero, so payments converge to pure premiums in large independent pools. This is the sense in which information aggregation produces diversification. The argument is robust and does not rely on special parametric families. This provides a precise operational interpretation for actuaries and risk managers. In practice, this clarifies what pool designs will actually deliver stability. The result is best read as an information theoretic averaging phenomenon. Under conditional mean risk sharing, participant I pays the expected value of their loss, conditional on the pool total. The first consequence is willingness to join. The conditional expectation is less dispersed than the original loss in the convex order sense, so every risk-averse agent prefers pooling to standing alone without committing to a specific utility function. The main monotonicity theorem says that when we add a new independent member, the conditional contribution of any existing member becomes smaller in convex order. The mathematical intuition is simple. The new loss does not reveal extra information about the old member, it only adds independent noise to the conditioning total. Conditioning on a noisier aggregate forces additional averaging of the conditional expectation. By Jensen's principle, additional averaging reduces dispersion in convex order while keeping the mean fixed. The second part is asymptotic. We analyze when the remaining variability disappears. We identify verifiable structural conditions under which the variance of conditional contributions converges to zero, so the contribution becomes essentially deterministic and equal to the pure premium in large pools. The motivation is peer-to-peer insurance and ex-post mutualization platforms. In such systems, claims are observed, then redistributed according to transparent rules that depend only on the realized total claim amount. The economic requirement is strong. The mechanism must be attractive to all risk-averse participants under a common dominance notion, not only on average, but in a robust sense. Conditional mean risk sharing meets this requirement. When the contribution as a function of the aggregate total is increasing, the rule is compatible with expected utility comparisons and can be shown to be Pareto efficient. No member can be improved without hurting someone else. Even without that monotonicity, convex order still gives a powerful benchmark for risk-averse preferences. We focus on independent losses because independence guarantees that enlarging the pool creates genuine diversification rather than informational revelation. The key intuition is that independence makes the aggregate less informative about any particular member. This informational dilution is what drives monotone risk reduction in convex order, and it also clarifies which structural distributional features are needed to move from reduction to elimination of residual risk. Operationally, the allocation rule can be viewed as a table. For each possible level of the aggregate loss, the rule assigns a contribution to each participant. This is why it is attractive for practice. It is transparent, deterministic once the total is observed, and it only requires knowledge of conditional expectations as functions of the total. From a theoretical standpoint, the key monotonicity condition is that the contribution increases with the aggregate loss. This condition is closely related to regression type dependence in sums and links our setting to classical monotonicity results for conditional expectations. When it holds, the allocation is consistent with risk-averse expected utility comparisons and achieves Pareto optimality. The probabilistic question we answer is, what happens to the conditional expectation of one component when we condition on a sum that includes more independent terms? The core mechanism is that enlarging the sum makes the signal coarser for any single component. So the conditional expectation becomes an average of earlier conditional expectations over additional independent noise. This produces convex order, monotonic diversification results that later translate into insurance pooling theorems. Convex order is the workhorse for our comparisons. Saying that one random variable is smaller than another in convex order means that every risk-averse agent prefers it. All concave utilities assign it a higher expected utility. Economically, the larger variable represents a mean-preserving increase in risk, so convex order captures pure dispersion at a fixed mean. A key reason convex order is so useful here is its stability under shifts and rescalings. If we add a constant or multiply by a positive number, convex order comparisons are preserved. This allows us to center contributions around their expectations and interpret results as statements about residual variability rather than about levels. In our context, the diversification statement pool enlargement helps is expressed as follows. The conditional contribution in the larger pool is smaller in convex order than in the smaller pool. This immediately implies a robust welfare improvement for all concave utilities, hence for all risk-averse participants. Convex order is therefore the exact mathematical bridge between probabilistic averaging effects and economic desirability of pooling mechanisms. The technical engine is a conditional mean independence principle. The idea is that if, after conditioning on a signal, adding another independent piece of information does not change the conditional mean of the variable of interest, then replacing the signal by a more aggregated version yields a conditional expectation that is less variable in convex order. The proof intuition uses nested conditioning. Conditioning on a coarser signal can be seen as taking an average of the conditional expectation given a finer signal, where the averaging is taken over the extra uncertainty that is forgotten when we coarsen. Because conditional expectations are already averages, this creates an average of averages. Jensen's inequality then tells us that such averaging reduces convex order dispersion while preserving the mean. Independence makes the condition easy to verify. If the extra term we add to the conditioning sum is independent of the variables already involved, it cannot reveal additional information about the component we are predicting. It only blurs the signal. This blurring is precisely what drives the monotone reduction in dispersion of conditional contributions when the pool expands by independent members. Specializing the previous mechanism to independent sums yields a clean result. When we condition on an aggregate that includes an additional independent term, the conditional expectation of a given component becomes smaller in convex order. The added term acts purely as independent noise, so the aggregate becomes a less precise indicator of the component we are trying to predict. The informational interpretation is central. The conditional contribution is the best prediction of an individual loss given the observed total. If we add an independent loss to the total, we do not gain information about the individual. Instead, we mix the signal with noise. The best prediction must then average over more plausible decompositions of the total, and that averaging reduces dispersion. The result extends beyond one participant. Considering two participants jointly, enlarging the pool improves the vector of contributions in a multivariate convex sense. This means not only that each marginal contribution becomes less variable, but also that joint fluctuations and dependence patterns weaken. For insurance pools, this formalizes that adding independent members improves stability, both at the individual and collective allocation levels. To obtain more operational criteria, we refine comparisons using convolution type dominance. The idea is that one remainder of the pool is larger than another in a structural sense if it can be represented as the smaller remainder plus an additional independent non-negative component. Under this dominance, conditioning on the larger remainder necessarily produces a conditional expectation that is smaller in convex order. Why is this structural requirement important? A simple statement like one remainder is more dispersed than another is not enough. Without independent structure, an enlarged aggregate could accidentally reveal the individual loss almost perfectly, destroying diversification. Convolution dominance rules this out. The extra variability enters independently and therefore guarantees genuine averaging rather than information revelation. In the insurance application, these dominance results provide checkable conditions. If in a growing pool, the rest of the portfolio contains many components that dominate a given loss in this convolution sense, then one can obtain explicit bounds ensuring that the dispersion of that participant's conditional contribution shrinks. This gives a concrete route to risk elimination based on distributional structure, not just on large N intuition. When the conditional expectation as a function of the aggregate is increasing, stronger ordering results become available. This monotonicity corresponds to a regression-type dependence and allows the use of size-biased ideas, which are probabilistic tools that reweight outcomes in proportion to loss size. The benefit is that they connect comparisons of conditional contributions to comparisons of weighted versions of sums. The quasi-proof intuition is as follows. Increasing conditional expectations allow us to compare risk-averse evaluations by checking how convex functions behave under these weighted distributions. Under appropriate dominance assumptions, one can show that a participant with smaller, mean and suitable size-biased dominance has a contribution that is smaller in increasing convex order than another participant's contribution. This is a refined fairness statement inside the pool. Economically, the key implication concerns tail risk. In large pools, risk management is driven by extreme aggregate outcomes. The monotonicity framework shows that adding independent members reduces not only overall dispersion, but also how much a given member contributes to extreme totals. Thus, diversification improves solvency-relevant tail measures, strengthening the case for CMRS in capital-sensitive insurance designs. We now turn to the insurance interpretation. Under conditional mean risk sharing, the contribution is the best mean square prediction of an individual loss given the aggregate. In homogeneous independent pools, symmetry implies that each member pays a proportional share of the realized total, so the rule reduces to simple averaging. The classical diversification intuition then follows. Averages become less variable as the number of independent terms grows. The heterogeneous case is the real target. Even without a closed form, the same structural mechanism applies. When a new independent participant is added, the conditioning total becomes noisier with respect to any existing member. The conditional contribution of that member becomes an average over more decompositions of the total, so it becomes smaller in convex order. This yields a monotone diversification theorem valid for every participant, irrespective of heterogeneity. Economically, this means that enlargement of an independent pool generates a uniform welfare improvement for all risk-averse agents. It also suggests that CMRS is a principled way to extend proportional sharing to heterogeneous peer-to-peer portfolios while retaining robust dominance guarantees and avoiding ad hoc allocation rules. A key structural step is to analyze the sequence of conditional contributions as the pool grows. This sequence forms a reverse martingale. As we add more independent losses to the sum, we condition on a coarser and coarser signal for any fixed participant, and the conditional expectations are nested in the reverse direction. The martingale machinery implies convergence both almost surely and in mean square to a limiting random variable determined by the long-run informational content of the aggregates. Risk elimination corresponds to the limit being deterministic. This happens when the tail information carried by ever larger aggregates becomes trivial, meaning that in the limit, the aggregate does not retain any non-trivial information about a single participant. In that case, the limit equals the pure premium, and the variance of contributions goes to zero. However, the paper shows that independence alone does not guarantee trivial tail information. If the support structure of one loss is distinguishable from the others, the aggregate can reveal that loss exactly, and the contribution remains as risky as the loss itself. This clarifies why structural distributional assumptions are essential for elimination. The paper then provides explicit sufficient criteria for elimination, expressed in terms that are meaningful for actuaries. A first mechanism is partitioning into homogeneous subclasses whose sizes grow proportionally with the pool. The intuition is within class averaging. If many nearly identical risks coexist, the aggregate contains less and less information about any one of them, and their conditional contributions stabilize. One can derive explicit bounds showing that the variability of a member's contribution shrinks at a rate governed by the growth of their class. A second mechanism relies on convolution dominance. If the rest of the pool contains enough components that dominate a given loss, in the structural convolution sense, then the conditional expectation becomes increasingly averaged over independent increments. This yields explicit variance bounds that decay reciprocally with a dominance index measuring how many such dominating components are present. These criteria are operational because they replace abstract tail sigma field arguments by verifiable portfolio structure. They tell practitioners how to design or select pools in which CMRS will not only reduce risk, but eliminate it asymptotically for each participant. Beyond elimination, the paper also studies comparative statics inside the pool. Under regression type monotonicity, participants can be ranked. Those with smaller mean losses and suitable dominance properties have conditional contributions that are smaller in increasing convex order. This provides a robust notion of actuarial fairness compatible with risk-averse preferences, not just with expected values. At the vector level, enlargement of the pool improves the joint distribution of contributions in a directionally convex sense. The intuition is that additional independent noise does not merely reduce each marginal dispersion. It also weakens co-movements. The allocation becomes more stable collectively because fewer aggregate scenarios create simultaneous upward pressure on many contributions. Economically, these joint results matter for perceived fairness and for budget management of the pool. Lower dependence between contributions means that large deviations are less synchronized across members, which stabilizes redistribution and reduces the likelihood of politically difficult outcomes where many members feel simultaneously overcharged. Thus, the stochastic order results translate into practical governance benefits for large peer-to-peer schemes. For implementation, the paper discusses a linear regression approximation of the conditional contribution. Practitioners often want a transparent formula depending only on first and second moments and the realized total. The regression rule provides exactly that. It approximates the conditional expectation by an affine function of the aggregate total, where the sensitivity coefficient reflects the relative variance of the participant compared with the portfolio. The mathematical intuition is projection. The conditional expectation is the best predictor given the total among all measurable functions. The regression approximation is the best predictor within the smaller class of affine functions. In large pools, regularity and averaging effects make the true conditional expectation close to linear in the aggregate, so the approximation becomes accurate. Economically, this is crucial. It allows a pool to communicate contributions using a simple and interpretable rule. Start from the pure premium and adjust according to whether the realized total is above or below its expectation, with weights proportional to individual variability. This maintains much of the diversification logic of CMRS while being operationally deployable in digital insurance platforms. To conclude, conditional mean risk sharing produces monotone diversification in convex order in independent pools. Each time an independent member is added, the aggregate becomes a noisier signal about any fixed participant. So the conditional contribution is forced to average over more decompositions of the total, reducing dispersion in the sense relevant for all risk-averse agents. The main conceptual advance is to identify when this monotone reduction becomes elimination. Under explicit structural portfolio conditions, such as sufficiently growing homogeneous subclasses or convolution-type dominance, the variance of conditional contributions converges to zero, so payments converge to pure premiums. The paper therefore provides a rigorous bridge from diversification as a qualitative intuition to elimination as a quantitative limit property. Future research should extend these criteria beyond independence, for example to exchangeable or mixture-based dependence structures, and should quantify residual risk when elimination fails. Another direction is to refine implementable approximations and study incentive and governance constraints in peer-to-peer schemes where transparency and perceived fairness are as important as mathematical optimality.